Welcome to the Midnight Lesson. If you have any ideas of topics for future sleepy lessons, drop them in the comments. I'm always looking for new suggestions. Now get comfortable, relax, and enjoy tonight's lesson on how the Grand Canyon was formed. There are places on Earth that feel less like scenery and more like revelation. Places that stop conversation mid-sentence. Places that force the human mind to do something it rarely does in daily life, which is to admit quietly and honestly that it cannot immediately understand what it is seeing. The Grand Canyon is one of those places. From the rim, it does not behave like a normal landscape. It does not sit politely in the distance like a mountain range or a coastline. It opens, it drops away, it interrupts the world. It looks like the planet has been split open and left exposed, as if someone peeled back the surface and revealed what was never meant to be seen. At first glance, it seems impossible. A canyon so vast it has its own weather, so wide that sound disappears into it, so deep that shadows stretch across miles of air before they ever touch stone. From one overlook you can see formations that look like temples, pyramids, and ruined cities. And everywhere, in every direction, the rock is layered like a stack of pages in an ancient book. Those layers are not decoration, they are evidence. The Grand Canyon is not simply a place, it is a record, it is a timeline turned vertical. It is the story of Earth, written in stone and opened to a single page that stretches for 277 miles. And yet, almost immediately. How did this happen? How does a landscape like this form? What force could carve a trench this immense into the crust of a continent? What kind of power is capable of removing that much rock, shaping it into cliffs and terraces, and leaving behind a masterpiece of geology that looks more like sculpture than erosion? Most people hear the simplest answer and accept it. A river did it. The Colorado River. It sounds almost ridiculous when you say it out loud. A river. Water moving downhill. The same kind of water that runs through garden hoses and taps. The same kind of water that can be held in a glass. And yet, here it is. A canyon that looks like the work of gods, attributed to a river that seems too small to deserve the credit. That contradiction is where the Grand Canyon begins. Not in the rock, not in the water, but in the tension between what the eyes believe and what the earth has actually done. Because the truth is, the Colorado River did carve the Grand Canyon, but it did not do it in the way most people imagine. This was not a single dramatic event, not one catastrophic crack in the ground, not a moment of collapse that created a void. The Grand Canyon was made through patience, through persistence, through the relentless physics of water, gravity, and time. And time, here, is the most important character in the story. The human brain struggles with deep time. It can handle minutes, hours, years. It can understand a lifetime, maybe a few generations. But the canyon is not built on that scale. The Grand Canyon is not old because it looks old. It is old because it contains time in layers, stacked one on top of another, each one representing a world that existed long before humans, long before mammals, long before forests, long before complex life itself. Some of the rocks at the bottom of the canyon formed nearly 2 billion years ago. 2 billion. That is not just old, that is almost half the age of the Earth. When those rocks formed, the planet was a stranger place. The atmosphere carried far less oxygen. The continents were arranged differently, if they existed in anything like the form we know today. Life was present, but simple, mostly microscopic, surviving in oceans that would have looked empty to the human eye. And yet, those rocks are still here. Not buried deep underground, not crushed beyond recognition, but exposed in canyon walls where you can stand above them and look down into an era that predates nearly everything familiar. Above those ancient basement rocks, layer after layer of sedimentary stone rises like a staircase through time. Sandstones that began as deserts, limestones that began as warm, shallow seas, shales and mudstones that began as quiet floodplains and deltas. Each layer once belonged to a different environment, a different climate, a different earth. This is why the Grand Canyon is not just impressive. It is scientifically priceless, because it is a cross-section of the planet's memory. In most places, Earth's history is hidden. Buried under soil, vegetation, and modern development, covered by younger rocks, eroded away, broken and folded, lost. The canyon is a window, it is also a warning. Because what it reveals is not stability. It reveals motion. It reveals that the world beneath our feet is not fixed. It changes. It rises. It sinks. It breaks. It reforms. The Grand Canyon looks permanent, but it is the product of change, and it is still changing. Even now, the canyon is widening. The walls are still falling in slow motion. The river is still grinding stone into sand and carrying it away. The landscape is still responding to storms, to temperature swings, to gravity pulling relentlessly at every cliff and ledge. The canyon is not a scar from the past. It is an ongoing event. But to understand how it formed, you have to start with a deeper truth. The Colorado River alone is not enough. A river can cut downward only if it has somewhere to go. It needs slope. It needs energy. It needs a reason to keep moving, to keep digging. That reason is elevation. The Grand Canyon exists because the land around it rose. Not suddenly, not violently like a volcano exploding upward, but steadily over millions of years as the Colorado Plateau lifted higher and higher above sea level. Imagine a giant slab of crust, thousands of feet thick, being raised like a stage. The rocks remained mostly flat and level, like a layer cake lifted into the sky. And as the plateau rose, rivers gained power. Water flowed faster. Gravity had more to work with. Every drop of rain that reached the ground had more potential energy than it used to. And when a river has more energy, it cuts deeper. The canyon is the result of that partnership, uplift and erosion. The land rises, the river responds. The river cuts down, the landscape collapses and widens. The river carries the debris away. The land continues to rise. The cycle repeats. This is the basic engine of canyon formation. It is not mysterious. It is not magical. It is geology doing what geology does, given enough time and the right conditions. But there is still something unsettling about it, because the Grand Canyon is too big, too clean, too structured. It looks intentional, and that illusion is what makes it so powerful. The canyon walls are not random. They are shaped by the nature of the rock itself. Hard layers form cliffs. Softer layers erode into slopes. Resistant sandstone holds up ledges like armor. Fragile shale collapses and retreats. Limestone breaks into steps and terraces. This is why the canyon has its iconic shape, with sheer walls and wide shelves, towers and buttes, sharp ridges and deep-side canyons branching like veins. The canyon is a sculpture, but the sculptor is physics, and the tools are water, wind, ice, and gravity. Still, even knowing that, you can stand at the rim and feel the question rise again. The answer depends on which part of the story you're asking about. The rocks themselves took hundreds of millions of years to accumulate. Some of them were formed in environments that lasted longer than the entire history of human civilization. Some were laid down grain by grain in slow cycles of deposition and burial, compressed into stone under the weight of the layers above. But the carving of the canyon, the cutting of the trench we see today, happened much later. Geologically speaking, it is young. The Grand Canyon, as a canyon, is thought to be carved mostly within the last 5 to 6 million years, as the Colorado River established a path and began cutting rapidly downward through the rising plateau. That is still an incomprehensible span of time to human minds. But compared to the age of the rocks it exposes, it is recent. It is as if someone opened an ancient book and ripped out a page in the last few moments, revealing everything inside. This is what makes the canyon unique. It is not just old, it is a collision between the ancient and the recent. The rocks are ancient, the canyon is young, and the forces that created it are still working. If you want to understand the Grand Canyon, you have to accept something that feels almost offensive to modern instincts. Nothing about it was meant to be fast. There is no single moment to point to, no day when the canyon formed, no dramatic beginning. Instead, there is accumulation. Burial, pressure, uplift, water, cutting, collapse, repetition. And in that repetition, something extraordinary emerges, a landscape that looks like catastrophe, built by persistence, a monument that looks like violence, created by patience, a place that feels impossible, made inevitable by physics. The Grand Canyon is not a mystery because we lack explanations. It is a mystery because we struggle to feel the scale of the explanation. We are not built to understand a million years. We are not built to imagine continents lifting. We are not built to picture rivers slowly soaring through rock like a blade that never dulls. But the canyon demands that we try, Because it is not only a landmark, it is proof. Proof that the Earth is older than we instinctively believe. Proof that slow processes can produce the most dramatic results. Proof that time is not just something we measure with clocks, but something that shapes worlds. Not just a canyon, not just a tourist destination, but a statement from the planet itself, a message carved into stone, a reminder that the ground beneath us is not a surface. It is a history. It is a story. And in the Grand Canyon, that story is exposed, waiting to be read. In the chapters ahead, we will read it layer by layer, era by era, force by force. We will move from ancient oceans to buried deserts, from continental collisions to rising plateaus, from the first trickles of a river system to the relentless carving of one of the greatest landforms on Earth. And by the end, the canyon will no longer feel impossible. It will feel inevitable. Because it was never formed in a moment. It was formed by the longest kind of power there is. Before the Grand Canyon was a canyon, before the Colorado River had a name, before the desert air shimmered above sun-baked stone, this region belonged to entirely different worlds, worlds that no human could survive in, worlds without familiar coastlines, without familiar skies, without familiar life. If you could travel backward in time far enough, you would not recognize this place at all. The story begins not with a chasm, but with a surface. A broad, ancient landscape that existed long before the canyon ever opened. A land that would be buried, compressed, transformed, and lifted again. A land that would be rewritten over and over, each version leaving behind traces, preserved like fingerprints in stone. To understand the Grand Canyon, you have to understand the time before it. Because the canyon itself is not the beginning of the story. It is the exposure of the story, the cutting that reveals everything that came before. And what came before was not one environment, but many. This part of North America has been a desert, but it has also been a coastline. It has been a seabed. It has been a floodplain. It has been a field of dunes. It has been a shallow tropical sea filled with life. It has been a quiet basin where mud settled slowly in still water. The Grand Canyon is famous for its depth, but its true power is in its layers. The canyon walls show us that the Earth does not stay one thing for long. It changes its mind. It changes its shape. It changes its climate. It changes its chemistry. It becomes something else. And the only reason we can read that transformation is because the canyon cut through it like a blade through a layered cake, exposing the inner structure of a world that would otherwise remain hidden. If you stand at the rim and look across, the canyon walls appear striped, bands of red and cream and brown, hard cliffs separated by softer slopes, terraces that step downward in giant shelves. Those stripes are not random. They are time. Each one represents a chapter of Earth's past, written in sediment and locked into rock. Each one began as loose material, sand, silt, mud, shell fragments and mineral grains, carried by wind or water, then dropped, then buried. It happened slowly, quietly, but over millions of years that slow accumulation becomes enormous. The oldest exposed rocks at the bottom of the canyon are not sedimentary layers at all. They are something deeper and older, rock that was altered under intense heat and pressure. But above them, stacked like a towering archive, are sedimentary layers that record hundreds of millions of years of changing environments. These layers tell a story of seas that advanced and retreated, deserts that expanded and collapsed, rivers that shifted course, coastlines that moved hundreds of miles over time. They tell a story of Earth in motion. To picture it, you have to imagine time not as a straight line, but as a repeating cycle. Water rises, water falls, sediment arrives, sediment settles, layers build, pressure increases, minerals lock together, stone forms. Then the cycle begins again. For long stretches of the past, this region was low and close to sea level. It sat on the edge of ancient continental interiors, where shallow seas could flood across vast areas when global sea levels rose. When those seas arrived, they brought life. Not the kind of life we think of first. Not forests, not mammals, not birds, but marine life. Shells, corals, crinoids, brachiopods. Creatures that drifted, crawled, filtered, and fed in warm, shallow water. When those creatures died, their shells and skeletons accumulated on the seafloor. Layer upon layer of calcium-rich debris settled into sediment that would eventually harden into limestone. This is one of the secrets of the canyon's pale cliffs and ledges. Some of those rocks were once living reefs and sea floors, and the evidence is still there if you know how to look. Fossil fragments embedded in stone, patterns in the rock that show wave ripples, the texture of ancient seafloor mud, the subtle signs of currents that moved across shallow water long before the canyon existed. Then, over time, the sea would retreat, not because the ocean drained away, but because sea level changed and the land itself shifted. Coastlines moved. What was once underwater became exposed to air again. The seabed dried out. Wind returned. Rivers returned. The environment transformed. In some periods, rivers carried sediment into broad plains. Mud settled in slow water. Sandbars formed and shifted. Floods spread silt across flatlands. Over time, these deposits formed layers of shale and mudstone, softer rocks that erode easily today, creating slopes and terraces in the canyon walls. In other periods, the region became arid, drier, hotter, wind-driven. Sand dunes marched across the landscape in massive fields, like a desert ocean. Grains of quartz rolled and bounced and piled into towering ridges. Over time, those dunes were buried and cemented into sandstone. This is how some of the canyon's most iconic cliffs were formed, not by rivers, but by wind. Some sandstone layers preserve the angled patterns of dunes frozen in place. Crossbedding, the diagonal lines that show the slope of ancient sand hills. They are unmistakable once you recognize them. They are the fingerprints of an ancient desert, and they tell us something important. The Grand Canyon is not the result of one environment enduring for ages. It is the result of environments changing dramatically, again and again. Tropical sea to coastal plain to desert, desert to shallow sea, over and over. This is why the canyon's layers are so varied. Each one formed under different conditions. Each one responds differently to erosion today. Hard layers stand tall, softer layers collapse. The canyon's stair-step profile is not just a matter of carving, it is a matter of material. Different rocks break differently. But there is another truth hidden inside these layers. There are missing chapters. In the canyon's rock record, there are places where time disappears, where the story jumps forward, where millions of years are absent. These gaps are called unconformities, surfaces where rock layers were eroded away or never deposited in the first place. They are pauses in the record, blank pages in the book. And some of those blank pages represent spans of time longer than the entire age of complex life on Earth. The most famous of these gaps is the Great Unconformity. In parts of the Grand Canyon, ancient metamorphic and igneous rocks nearly 2 billion years old sit directly beneath much younger sedimentary layers that are only about 500 to 600 million years old. That means more than 1 billion years of time is missing. Gone. Not because it never happened, but because the evidence was erased, eroded away by ancient landscapes that no longer exist. The Great Unconformity is one of the most dramatic breaks in Earth's visible history anywhere on the planet. And in the Grand Canyon, it is exposed in a way that is almost shocking. It is the planet showing you that even its memory is incomplete. Even stone can forget. But when the record resumes above that gap, it reveals a world that is changing in a different way. Around 540 million years ago, life on Earth undergoes one of the greatest explosions of diversity in its history. In the oceans, complex organisms multiply rapidly. Body plans evolve. Shells and skeletons become more common. Predation begins to shape ecosystems in new ways. This is the Cambrian explosion. The rocks above the Great Unconformity, particularly the layers deposited in shallow marine environments, begin to carry more abundant fossils. Traces of early marine animals, burrows, tracks, shell fragments. The canyon becomes not only a record of geology, but a record of life. The story of the Grand Canyon is not just the story of rock. It is the story of worlds that lived and died here, long before humans existed. It is the story of ecosystems that rose and vanished as environments shifted. It is the story of Earth as a living planet, constantly rewriting its surface. And through it all, one thing remained true. Sediment kept arriving, the land kept being shaped. Layer after layer continued to build, but the canyon itself still did not exist. There was no deep chasm, no mile-deep void, no dramatic drop, just a landscape changing gradually over time, sometimes underwater, sometimes above it, sometimes flat, sometimes eroding, sometimes accumulating. For most of this history, the region that would become the Grand Canyon was not a dramatic place. It was not a landmark. It was part of a larger, quieter world, a surface that rose and fell gently with changing seas and shifting climates. The canyon was not inevitable yet, because for a canyon to form, you need something more than layers. You need energy. You need uplift. You need a reason for water to cut downward instead of spreading outward. You need the land to rise high enough that gravity can turn rivers into chisels. That part of the story comes later, but the foundation had to be built first, and that foundation was built in slow motion, grain by grain, shell by shell, flood by flood, dune by dune. For hundreds of millions of years, the Earth stacked environments on top of one another, compressing them into rock, preserving them as a layered archive. The result was a thick, diverse sequence of sedimentary stone that would one day be exposed to the sky. And that is what makes the Grand Canyon different from many other landscapes. It is not just a hole cut into rock. It is a hole cut into history. If you could somehow remove the canyon and flatten the layers back into a solid surface, you would still have something remarkable. A massive, ancient stack of Earth's past, hidden underground like a library sealed in stone. But the canyon did form, and when it did, it exposed everything. It turned buried time into visible walls. It transformed a hidden archive into one of the most famous landscapes on Earth. It gave humans the rare chance to see what the planet is really made of. Not soil, not grass, not trees, not cities, but deep structure. The raw material of continents. The record of oceans and deserts, floodplains and coastlines. The evidence that Earth is not stable, not fixed, not permanent. It is alive in the slowest way possible, and the Grand Canyon is where that slow life is revealed. In the next chapter, we will descend to the bottom of the canyon and begin with the oldest visible foundation, the rocks that formed deep within the Earth long before the layers above them existed. Because before there were seas, before there were deserts, before there was even a recognizable North America, there was something deeper, a basement of stone, a beginning written in heat and pressure, and it is still there, holding up everything above it. To understand the Grand Canyon, you have to go down, not just down in elevation, but down in time. From the rim, the canyon looks like a single landscape, one enormous space, one sweeping view. But the deeper you descend, the more the canyon changes. The walls close in. The air warms. The rock shifts color and texture. The layers that look like thin stripes from above become towering cliffs and slopes you can stand beside. And eventually, after miles of descent, the canyon stops looking like a stack of sedimentary layers and begins to look like something else entirely. Darker, harder, older. At the bottom of the Grand Canyon, the rock is not arranged like pages in a book. It is not neatly layered sandstone and limestone. It is twisted, folded and scarred. It looks like the Earth has been through violence, because it has. This is the basement of the continent, the foundation, the oldest exposed rock in the Grand Canyon and among the oldest visible rocks anywhere in North America. Here, in the depths, you are no longer looking at the remains of ancient seas and deserts. You are looking at rock that formed deep inside the planet, under conditions that no surface environment could produce. Rock that began as something else, then was transformed by heat and pressure until its original identity was nearly erased. This is where the canyon's story becomes truly ancient. The dark, jagged rock that forms the inner gorge is known as the Vishnu basement rocks. They include the Vishnu schist, along with intrusions of Zoroaster granite and other igneous bodies. Their names sound almost mythic, and in a way they are, because these rocks come from a world that existed so long ago that the Earth itself was still settling into its modern form. The Vishnu schist is roughly 1.7 to 1.8 billion years old. To put that in perspective, the Grand Canyon as a canyon is only a few million years old. The sedimentary layers above the basement rocks span hundreds of millions of years. But these basement rocks are more than a billion years older than most of what sits on top of them. They formed long before animals, long before plants, long before the oxygen-rich atmosphere we breathe today. When the Vishnu schist was forming, the world was a different planet. The continents were smaller and more scattered. The oceans were chemically different. The sky carried less oxygen and more volcanic gases. Life existed mostly as microscopic organisms living in water, leaving faint traces in sediment and chemistry. There were no forests, no birds, no dinosaurs, no mammals, not even the first fish, and yet the rock beneath your feet was already forming. But the Vishnu schist did not begin as schist. Schist is a metamorphic rock, meaning it was changed, transformed, rebuilt. Long ago, the material that would become the Vishnu schist likely began as volcanic rock, sediment, and oceanic crust. It may have formed in island arcs and marine basins, in a world where tectonic plates were colliding and assembling pieces of crust into larger landmasses. Then those materials were buried deep, squeezed and heated, caught in the machinery of plate tectonics. Pressure aligned minerals into shimmering plains. Heat rearranged the crystal structure of the rock. Original textures were destroyed and replaced. The rock became foliated, meaning it developed a layered fabric, not from sediment settling, but from minerals being forced to align under stress. That is why Vishnu schist looks so different from the sedimentary layers above it. It does not represent calm deposition. It represents deep transformation. It is rock that has been through the Earth's internal furnace. And this is one of the most important points in the canyon's story. The Grand Canyon is not only a record of surface environments, it is also a record of deep Earth processes. It contains evidence of the planet's interior forces, the collisions and compressions that build continents. If you stand in the inner gorge, surrounded by dark metamorphic walls, you are standing inside the foundation of North America. But the Vishnu schist is not alone down there. Cutting through it are lighter-colored veins and bodies of granite, known as the Zoroaster granite. These granite intrusions are slightly younger than the schist, around 1.4 billion years old. Granite forms from molten rock, magma, that cools slowly underground. Unlike lava, which erupts onto the surface and cools quickly, granite forms deep below, where heat escapes slowly and crystals have time to grow large. The presence of granite, intruding into the schist, tells us something crucial. After the Vishnu schist formed and metamorphosed, the region was still tectonically active. Magma rose through cracks, forcing its way into the older rock, cooling into granite that now appears as pale bands cutting across the darker schist. This is how geologists can read the sequence of events. The schist had to exist first, because the granite cuts through it. The granite is younger because it intruded later. The canyon walls preserve that relationship clearly, like a frozen moment of intrusion captured in stone. In the inner gorge, you can see these relationships with your own eyes. Dark, folded metamorphic rock intersected by lighter granite veins. A network of ancient injections, solidified in place. It is a reminder that the Earth is not built in layers alone. It is built in episodes, in pulses of heat, in cycles of collision and melting, in moments when crust thickens and then partially liquefies. This is how continents grow, not in a single event, but in fragments that collide, weld together, and harden over immense spans of time. The Vishnu basement rocks are evidence of one of those ancient continental debuilding events. They likely formed during a period of mountain building known as the Yavapai orogeny, when pieces of crust collided and assembled into a larger landmass. The word orogeny means mountain building, but it is not mountain building like we picture today, with visible peaks and ridgelines. This is mountain building at a scale and depth that reshapes the crust from within. When crust collides, it thickens. When it thickens, it heats. When it heats, it metamorphoses. When it becomes hot enough, parts of it melt, generating magma that can intrude upward. This is a continent being forged, and the evidence is still visible in the canyon's depths. But there is something else the basement rocks tell us. They tell us that the canyon's story is not continuous, because above the Vishnu basement rocks there is a gap, a missing chapter so enormous it is almost difficult to accept. In many parts of the canyon, the Vishnu schist and Zoroaster granite are overlain by much younger sedimentary layers with more than 1 billion years of time missing in between. This gap is part of what is known as the Great Unconformity. It represents a span of time where the rock record was erased. Either nothing was deposited or whatever was deposited was later removed by erosion. Imagine an entire era of Earth history, longer than the time separating humans from the first dinosaurs, simply gone from the visible record. That is what this unconformity represents. And it forces a strange realization. Even the Grand Canyon, famous for revealing Earth's history, cannot reveal all of it. Some of it is missing forever. But that missing time is not empty. It was filled with events, with erosion, with shifting continents, with changing climates, with the slow wearing down of ancient mountains. Because after the basement rocks formed, the region did not remain buried deep underground forever. At some point, the crust was uplifted and exposed. Mountains that once existed above these rocks were eroded away. The land was worn down closer to sea level. For immense spans of time, the surface was scraped and flattened by weathering and erosion, and then much later, sedimentary layers began to accumulate on top of that ancient foundation. That is why the basement rocks are at the bottom, not because they started there, but because everything above them came later. The canyon reveals a fundamental truth about Earth's surface. It is recycled. Mountains rise, then vanish. Continents shift, then break apart. Basins fill, then are carved open. Nothing stays the same. The Grand Canyon is a rare place where the planet allows us to see both the deep foundation and the later layers built on top of it. It is like seeing both the skeleton and the skin. But the basement rocks are not easy to reach, and they are not easy to read. They are rugged, complex, and resistant. They do not break neatly like sandstone. They do not show obvious fossils. They do not record ancient shorelines. Instead, they record stress. They record heat. They record pressure. They record the deep forces that built the crust long before the surface world looked anything like it does now, and they influence the canyon's shape even today. The inner gorge is steep and narrow compared to the wider canyon above. That is partly because the basement rocks are harder and more resistant to erosion than many of the sedimentary layers above them. The river has cut through them, but it does so in a tighter, more confined channel. In other words, the canyon changes shape because the rock changes. Even the river must obey the nature of the stone it cuts through. Standing at the bottom of the Grand Canyon, surrounded by Vishnu schist, you are not just at the bottom of a canyon, you are at the edge of a deep time boundary. Above you is the layered record of oceans, deserts, and coastal plains. Below you is the foundation of a continent, forged in ancient collisions, and between them is a missing billion years. That gap is not just a geological curiosity. It is a reminder that Earth's history is not always preserved. It is a reminder that the planet is constantly rewriting itself, erasing old chapters as it creates new ones. The Grand Canyon is often described as a book of time. But even books can have torn pages. Still, what remains is more than enough to humble anyone who sees it. Because the Vishnu basement rocks represent something that feels almost impossible to grasp. They represent a time when the Earth was young, when the continents were still assembling, when the surface was still evolving toward the world we know. They are not just old rocks. They are the deep foundation of the land itself. And the canyon, by cutting down to them, gives us the rarest kind of view. A view into the making of a continent. In the next chapter, we will climb upward from the basement rocks into the stacked sedimentary layers above, where ancient seas and deserts left behind the famous stripes of the canyon walls. Because once the foundation was in place, the Earth began to build on top of it, layer by layer, world by world, until the stage was finally set for the force that would carve it all open, the river and the canyon itself. Above the dark, twisted basement rocks of the inner gorge, the Grand Canyon changes character. The jagged, metamorphic walls give way to something more orderly, more structured, more readable. Here, the rock begins to stack in layers. Bands of red, tan, grey, and cream rise above the river like a towering archive. From a distance, these layers look like stripes painted across the canyon walls. Up close, they become cliffs you can touch, slopes you can walk across, ledges that stretch for miles. This is the Grand Canyon most people recognize. Not the chaotic basement of a continent, but the layered record of ancient environments laid down over hundreds of millions of years. A sequence of sedimentary rocks that formed at the surface, in deserts, in rivers, in coastal plains, and beneath warm, shallow seas. Each layer is a world that no longer exists. And yet, the evidence is still here. To understand these layers, you have to remember what sedimentary rock really is. Sedimentary rock is made from pieces of older material, grains of sand, particles of silt, clay, bits of shell, tiny fragments of minerals and life transported by wind or water, then dropped, then buried. Over time, those loose materials become compacted. Water is squeezed out. Minerals precipitate and cement grains together. The sediment becomes stone. The process is slow, but it is relentless, and over millions of years it creates something extraordinary. It creates a timeline you can walk through. In the Grand Canyon, the layers above the basement rocks span roughly 1.2 billion years of Earth history, from the Proterozoic into the Paleozoic era. Not every layer is present everywhere. Not every time period is recorded, but the canyon preserves enough to tell a sweeping story of shifting seas, advancing deserts, and changing climates. And the canyon's shape, its stair-stepped cliffs and terraces, is shaped by the nature of those layers. Hard layers resist erosion and form cliffs. Softer layers break down and form slopes. Some layers fracture into blocks, others crumble into dust. The canyon is not carved into a uniform material. It is carved into a stack of different worlds, each with its own strength, its own texture, its own story. One of the first major sedimentary units above the basement rocks is a sequence known as the Grand Canyon Supergroup. These rocks are older than the more famous Upper Canyon layers and represent a time when the region was collecting sediment in basins that formed as the crust stretched and shifted. These layers include sandstones, shales, and limestones that record ancient shorelines, tidal flats, and shallow marine settings. In places, the supergroup rocks are tilted. That detail matters. Most of the sedimentary layers higher in the canyon are relatively flat, like a cake baked in a level pan. But the supergroup layers were disturbed. They were tilted by tectonic forces long before the younger layers were deposited on top of them. That tilt tells us that even during this earlier time, the region was not stable. The crust was moving. Basins formed. Sediment filled them. Then the basins were uplifted and tilted. Then erosion planed them down again. The earth kept rearranging the stage. And above this older sequence comes one of the most dramatic boundaries in the canyon, a line that separates vastly different ages of rock, a surface that represents missing time, the great unconformity. In many parts of the Grand Canyon, the younger, flatter sedimentary layers sit directly on top of older rocks that were tilted, eroded, and exposed for immense spans of time. The contact is sharp and unmistakable. Flat layers above, tilted layers below, time missing in between. It is the planet showing you a pause, a reset, a break in the record. And then, above that break, the canyon becomes a more continuous story again. Layer upon layer of Paleozoic rock rises upward, and with it comes a clearer record of changing environments. One of the first major formations in this upper sequence is the Tapeats sandstone. It often forms a prominent ledge, a thick band of resistant rock that stands out in the canyon walls. The Tapeats sandstone is significant, not just because it is visible, but because it marks the return of the sea. This sandstone was deposited as the ocean advanced across the continent, flooding low-lying land and laying down sand along shorelines and shallow coastal waters. If you could stand here during Tapeats time, you might see waves, tidal currents, beaches, sandbars, a coastline stretching far into the distance. This was not the Grand Canyon. This was the edge of a shallow sea. The Tapeats sandstone is a shoreline frozen into rock. Above it lies the bright Angel Shale, a softer, finer-grained layer that often forms slopes rather than cliffs. Shale forms from mud. Mud settles in calmer water, where fine particles can drift down slowly and accumulate. The presence of shale above the sandstone suggests that the sea deepened or the environment became quieter. Instead of pounding surf and shifting sand, you have lower-energy water where mud can settle. This is how geologists reconstruct ancient environments, not from imagination but from evidence. Coarse grains mean higher energy, finer grains mean lower energy. The rock is a fingerprint of the conditions that created it. Above the Bright Angel Shale sits another major unit, the Muavi limestone. Limestone forms when calcium carbonate accumulates, often from shells and marine organisms, or from chemical precipitation in warm, shallow seas. Its presence suggests a thriving marine environment. This sequence, sandstone to shale to limestone, is a classic pattern in geology. It reflects a marine transgression, an advancing sea. First the shoreline sands, then deeper water muds, then widespread carbonate deposition in warm, shallow water. The canyon walls preserve that transition like a slow-motion film, and it is not just a story of water. It is a story of life. Even though the canyon's older layers are ancient, they contain traces of marine organisms, especially in the limestone units. Fossils and fossil fragments appear as subtle textures, patterns, and embedded remains. These are the remnants of creatures that lived in seas that covered this land long before any vertebrate ever walked on Earth. As you move upward in the canyon, you continue to pass through environments that changed again and again. At times the region returned to coastal plains. At times it became more arid. At times shallow seas returned. The canyon's layers do not represent a single long ocean era or a single long desert era. They represent cycles: sea, then land; wet, then dry; shallow water, then dunes; floodplains, then coastlines. One of the most iconic and visually striking formations in the Grand Canyon is the Red Wall limestone. Despite its name, it is not naturally red. The limestone itself is gray. It appears red because it is stained by iron-rich sediments washed down from above, painting the cliff face with color. The red wall forms massive vertical cliffs, thick and resistant, towering above the layers below. It represents a time when the region was again submerged beneath a warm, shallow sea, where carbonate sediments accumulated over immense time spans. The red wall limestone is a reminder that some of the canyon's most dramatic walls were once quiet sea floors. Above the red wall, the canyon transitions into more varied layers again, including sandstones, shales, and limestones that reflect shifting environments. Then comes a layer that feels almost like a signature: the Coconino sandstone. This formation is famous for its pale color and its sweeping cross-bedded patterns, the angled lines that record the movement of ancient sand dunes. The Coconino was formed in a desert. Not a small desert, but a vast one. A dune field stretching across a landscape that was dry, wind-driven, and immense. If you could stand here during the time of the Coconino, you would not see a sea. You would see sand. Endless ridges of dunes migrating across the horizon. The air would be dry, the wind would be constant, the surface would shift beneath your feet, and the dunes would move, slowly but steadily, driven by wind over thousands of years. Those dunes were eventually buried and turned into stone, preserving their shape in angled layers. This is one of the most powerful things about the Grand Canyon. It allows you to stand in one place and see evidence of oceans and deserts stacked on top of each other, separated by time but preserved in rock. A seafloor below. A desert above. The planet changing its mind again and again. But the layers do not simply sit there as a neat stack. They interact with the forces that carve the canyon. Hard sandstones like the Coconino resist erosion and form steep cliffs. Softer shales crumble and retreat, creating slopes. Thick limestones form massive walls. This is why the canyon has its terraced appearance. The canyon is shaped by differential erosion. Some layers erode quickly, some erode slowly, and as the river cuts downward, the walls respond according to what they are made of. The canyon is not carved into a single material. It is carved into a complex architecture of strength and weakness, and that architecture controls the shape of the land. This is why the Grand Canyon looks the way it does. Not just because a river cut it, but because the rock stack it cut through contains alternating hard and soft layers, each responding differently to weathering and gravity. And gravity is always at work here. Even without the river, the canyon would change. Rock expands and contracts with temperature swings. Water enters cracks, freezes, and pries them wider. Rainstorms trigger rockfalls. Entire blocks detach and tumble into the canyon below. Over time, the walls retreat, the canyon widens, the river cuts down, the walls fall back. This is how a canyon grows, downward and outward, and the canyon's layers, each representing a different world, become part of the machinery of its own destruction. The very archive that records Earth's past is also being dismantled by the forces of the present, but that dismantling is slow enough that the record remains readable. For now. And in that record there is something profound. The layers show that the Grand Canyon was not built for the canyon. These rocks were not formed in anticipation of being exposed. They were formed as normal environments, in normal geological processes, over immense spans of time. They were built as a foundation, a thick stack of sedimentary history. And then, much later, the canyon cut into them. The canyon is not the creator of these layers. It is the revealer. It is the reason we can see them at all. Without the canyon, these worlds would be buried, hidden beneath younger rock, invisible to us, a window into the deep past. And as you climb higher through the layers, you are climbing forward through time. moving from ancient seafloors to coastal plains, from mud deposits to dunes, from limestone cliffs to sandstone ledges. Each step upward is a step toward the modern world, but the canyon itself still has not formed yet, not in this chapter, because these layers are the stage, not the action. They are the material that will be carved. They are the archive that will be opened. The canyon story requires one more crucial ingredient. The land must rise. The plateau must lift high enough to give rivers power. Only then can the Colorado River become more than a river. Only then can it become a cutting force. In the next chapter, we will step away from the layers and look at the forces beneath them, the tectonic machinery that reshaped Western North America and set the stage for uplift. Because the canyon is not just about erosion, it is also about the land rising to meet the knife of water. And when that uplift begins, the story shifts from ancient environments to unstoppable forces. The slow rise of a plateau and the making of a canyon. Seas advanced and retreated, deserts rose and vanished, rivers wandered across plains, sediment piled up layer by layer until the region became a thick archive of stone. But the canyon itself still did not exist, because sediment alone does not make a canyon. To carve a chasm this deep, you need something else. You need the land to rise. You need elevation. You need energy. And elevation is not created by wind or waves. It is created by the deep forces of the earth, by tectonics, by the slow but unstoppable movement of plates that reshape continents over millions of years. The Grand Canyon is often explained as a triumph of erosion, a river cutting through rock, water doing what water does. But erosion is only half the story. The other half is uplift. The Earth's outer shell is not one solid piece. It is broken into enormous slabs of crust and upper mantle, tectonic plates drifting across the globe at speeds measured in centimeters per year. That movement sounds small, but it never stops. Plates collide and mountains rise. Plates separate and basins open. Plates slide past each other and faults tear through the crust. The continents we know today are the result of those slow motions, repeated and relentless. North America itself is not a single ancient block. It is a collage, a continent assembled from fragments, pieces welded together by collisions that happened long before the Grand Canyon existed. And even after those early collisions formed the continent's foundation, the western edge of North America remained active, unstable, and constantly changing. Because the west coast of a continent is often where the action happens. That is where plates meet. That is where oceanic crust dives beneath continental crust. That is where the surface is compressed, thickened, heated, and uplifted. This process is called subduction. An oceanic plate, dense and heavy, sinks beneath a lighter continental plate. As it descends, it drags the edge of the continent downward, while also creating melting deep underground. That melting feeds volcanoes and intrusive magma bodies. Meanwhile, the compression squeezes the crust, building mountain ranges. Subduction is one of the main engines of mountain building on Earth. And for much of the last 200 million years, subduction has shaped the western margin of North America. During the age of dinosaurs, the West was not what it is today. The coastline was different. The mountains were different. The landscape was in motion, and beneath it all, an oceanic plate was diving under the continent. The consequences of that subduction were enormous. It thickened the crust. It generated volcanic arcs. It built mountain ranges. It reshaped the interior of the continent. It created basins that filled with sediment and uplifts that rose above them. It did not create the Grand Canyon directly, but it changed the continent in ways that made the canyon possible later. One of the key outcomes of subduction is that it can create uplift far inland, not just at the coast. The forces are transmitted through the crust like stress through a beam. Over time, huge regions can rise or warp upward, changing drainage patterns and creating new gradients for rivers. And rivers respond to gradients. If land rises, rivers cut down. If land sinks, rivers slow and deposit sediment. This is the basic relationship that connects tectonics to erosion. Tectonics builds the stage. Erosion performs the cutting. In the American West, this relationship has been playing out for tens of millions of years, and it includes a major turning point. For a long time, the western edge of North America was dominated by compressional forces. The crust was being squeezed, thickened, piled upward. But eventually the tectonic regime changed. Instead of compression, parts of the western interior began to stretch. The crust began to pull apart. This is extension. Extension does not build mountains the same way compression does. Instead, it thins the crust, creates fault block ranges, and opens basins. It breaks the land into long, tilted blocks separated by faults. This stretching helped form the Basin and Range Province, the region of alternating mountain ranges and valleys that stretches across much of Nevada and into surrounding states. And that stretching mattered for the Grand Canyon because it altered the western landscape in ways that would eventually affect how rivers flowed, where water could escape, and how the Colorado River system would evolve. But the most important tectonic factor for the Grand Canyon is not the stretching far to the west. It is the uplift of the Colorado Plateau. The Colorado Plateau is a massive region of relatively intact crust, covering parts of Arizona, Utah, Colorado, and New Mexico. It is known for its high elevation, its broad, flat-lying sedimentary layers, and its dramatic canyon landscapes. Unlike the Basin and Range, the plateau did not break apart into tilted blocks. It rose as a large, coherent region. It lifted upward without being intensely folded or crushed. That is one of the reasons the Grand Canyon is so readable. The layers remained mostly flat. They did not become twisted and mangled like mountain belts. Instead, they rose as a thick stack, elevated high above sea level. This is what made the plateau a perfect target for river incision, because when you lift a landscape, you increase the potential energy of every drop of water that flows across it. Water wants to reach sea level. Gravity demands it. So when the plateau rises, rivers begin to cut. They respond by digging downward, carving channels deeper into the rock, trying to re-establish a balance between slope and flow. This response is called downcutting, and downcutting is the first step toward canyon formation. But uplift is not a single switch that flips on. It is a complex, multi-stage process that can occur for different reasons. Some uplift comes from crustal thickening, when compression makes the crust buoyant and high. Some comes from heating of the lithosphere, which makes it expand. Some comes from mantle dynamics, deep changes in the flow of hot rock beneath the plates that can push regions upward. The exact causes of Colorado Plateau uplift are still studied and debated, but the evidence is clear that the region rose significantly over the last 70 million years, and especially over the last 20 to 30 million years. That uplift changed everything. Before uplift, the region was lower, and rivers behaved differently. Drainage systems may have been internal, flowing into basins instead of cutting outward. Water may have spread across plains instead of carving deep channels. After uplift, the rules changed. Rivers gained power, and the land became vulnerable, because a high plateau is stable only as long as it resists erosion. Once rivers begin cutting into it, the process accelerates. Channels deepen, tributaries grow, slopes steepen, and mass wasting begins. Rockfalls and landslides widen valleys. The landscape begins to dissect. In other words, uplift creates relief. Relief is the difference between high and low elevation. And relief is what allows dramatic landscapes to exist. Without relief, there is no canyon. The Grand Canyon required a high plateau. It required the land to rise. But tectonics did something else too. It created fractures, faults and joints in the rock. These cracks may be invisible from a distance, but they matter. Water exploits weaknesses. Erosion prefers paths of least resistance. Fractures guide the growth of tributaries. They influence where cliffs break, where side canyons form, where the canyon widens. The canyon's shape is not random. It is partly controlled by the internal structure of the rock, shaped by tectonic stresses over long spans of time. This is why the canyon is not a simple straight trench. It bends, it branches, it forms side canyons that reach deep into the plateau. It follows weaknesses in the rock. The Colorado River did not cut wherever it wanted. It cut where it could, and where it could was shaped by the tectonic history of the region. So the Grand Canyon is not a story of water alone. It is a story of water acting on a landscape prepared by tectonics. A landscape lifted into the sky, a landscape fractured and structured, but there is still a problem. Even with uplift, you still need a river system capable of cutting through the plateau. You need water flowing consistently. You need sediment to grind the bedrock. You need a drainage network that connects from high elevations to low. And for the Colorado River, that network did not always exist. The modern Colorado River system, flowing from the Rocky Mountains to the Gulf of California, is the result of a complex evolution. It formed through the integration of smaller drainage basins over time, linking them into a single powerful river that could carve downward. In other words, the river had to become a river. It had to assemble itself, because a plateau can rise for millions of years, and nothing dramatic will happen unless water finds a path across it. Once water does, the cutting begins. And once the cutting begins, it is hard to stop. In the next chapter, we will focus on that uplift directly. The rise of the Colorado Plateau, how it changed the landscape, and why it turned a region of layered rock into a stage ready for one of the greatest erosion events on Earth. Because the canyon was not carved until the stage was lifted, and once it was lifted, gravity did the rest. Slowly, relentlessly, one drop at a time. A canyon is not just a hole in the ground. A canyon is an imbalance. It is what happens when a landscape is given too much height, too much slope, too much energy, and water is allowed to respond. That is why the Grand Canyon could not form until the land itself rose. Because before the river could carve downward, it needed gravity to work in its favor. It needed elevation. It needed a stage high enough that water would cut instead of wander. That stage is the Colorado Plateau. Today, the Colorado Plateau covers a vast region of the American Southwest, stretching across northern Arizona, southern Utah, western Colorado, and northwestern New Mexico. It is a land of high deserts, mesas, cliffs, and deep canyons. A place where rock layers lie stacked like a thick archive, lifted thousands of feet above sea level. But it did not always sit this high. For much of its history, the plateau existed as a lower landscape, shaped by shifting seas and sedimentation. It accumulated layers for hundreds of millions of years, building a thick sequence of sedimentary rock above the ancient basement. Then, over time, something changed. The plateau began to rise, not as a jagged mountain belt, not with the intense folding and crushing that creates the Rockies or the Himalayas, but as a broad, coherent region. A giant block of crust lifting upward while remaining relatively intact. This is one of the most remarkable features of the Colorado Plateau. It rose without being destroyed. The rock layers stayed mostly flat, like a stack of books lifted onto a shelf. And that matters because it means the plateau preserved its layered record. It kept the canyon walls readable. It kept the story intact. It is slow, measured in millimeters per year, but it is steady, and over millions of years it becomes enormous. The Colorado Plateau rose thousands of feet. That rise did not happen all at once. It occurred in stages over long spans of time, driven by deep processes that are still studied today. Some uplift is linked to crustal thickening, where compression makes the crust buoyant and high. Some is linked to changes in the mantle, the hot, slowly moving rock beneath the plates, which can push the surface upward. Some may be linked to the removal of dense lithosphere beneath the plateau, allowing the region to float higher like a boat losing weight. The exact details are complex, but the outcome is simple. The land rose, and when the land rises, rivers change. Water flows downhill. It always has. It always will. But the power of a river depends on its gradient, the steepness of its path. A river on a flat plain moves slowly, spreads out, and deposits sediment. A river on a steep slope moves faster, concentrates energy, and cuts into its bed. The difference is not subtle. It is the difference between building land and destroying it. The Colorado Plateau uplift gave rivers the ability to destroy. It gave them the energy to cut down through rock instead of simply flowing across it. This is the moment the canyon becomes possible, because a canyon is a river's response to uplift. If the land rises faster than the river can adjust, the river incises. It cuts downward, carving a deeper channel to maintain its path toward lower elevation. That incision is the first cut, and once incision begins, it triggers a chain reaction. As a river cuts down, the valley walls become steeper. Steeper walls are less stable. Gravity begins pulling rock toward the channel. Slopes collapse. Side streams cut into the plateau and join the main river. The drainage network grows, expanding like roots into the surrounding land. The canyon widens. Not just because the river cuts, but because the walls fall back. This is how deep canyons become wide canyons. Downcutting creates depth. Mass wasting creates width. Together they shape the Grand Canyon. But to appreciate what uplift really did, you have to imagine the plateau before the canyon existed. Picture a high, broad region of layered rock, a surface that might have looked like a gently rolling landscape, perhaps broken by cliffs and mesas, but not yet dissected by a single massive chasm. Now lift that surface upward. As the plateau rises, every stream becomes more aggressive. Every rainstorm becomes more consequential. Every seasonal melt carries more energy. Water begins to find weaknesses, fractures, and low points, and it exploits them. It begins to carve. But the Colorado Plateau is not uniform. It did not rise perfectly evenly. Different parts rose at different rates. Some areas uplifted more, some less. Some tilted slightly, some fractured. Faults and joints formed, creating pathways for erosion to accelerate. The plateau's uplift was broad, but not perfectly smooth. And those subtle differences influenced where rivers cut fastest, where tributaries grew, and how the landscape broke apart. In the Grand Canyon region, the plateau rose high enough that rivers could begin to incise rapidly. But there is another critical factor. Uplift alone is not enough. You need water. A lot of it. Not necessarily in constant rainfall, but in sustained river flow over long time spans. A river must persist. It must continue to carry sediment. It must keep moving material out of its channel. Because rivers do not cut rock with water alone, they cut rock with tools. Sediment is the tool. Sand, gravel, cobbles, even boulders, carried by the river, grind against the bed like sandpaper. They strike the rock, scrape it, wear it down. During floods, this grinding intensifies. The river becomes a moving belt of abrasion, scouring the channel deeper. Without sediment, a river can still erode chemically, dissolving some minerals, but the dramatic carving of a canyon requires physical abrasion. The Colorado River became a cutting machine because it carried sediment, and because it flowed with enough energy to use that sediment as a weapon. And uplift made that energy possible. But uplift also created a new problem for the landscape. It increased erosion everywhere, not just in the river channel. As the plateau rose, the climate and weathering patterns changed. Higher elevation affects temperature. It affects precipitation patterns. It affects snow accumulation in the mountains that feed rivers. It affects the intensity of storms. Over millions of years, climate shifts combined with uplift to shape how much water entered the river system and how often major flood events occurred. The canyon is the result of both. The river's long-term flow and the violent pulses of floods that accelerate erosion. If uplift is the stage being raised, climate is the lighting. It changes how the story looks and how fast it moves, but even with uplift and water, there is still a missing piece. The modern Colorado River, flowing from the Rocky Mountains to the Gulf of California, did not always exist as a single continuous river. It had to form. It had to connect. In its early history, the drainage in this region may have been broken into separate basins. Streams may have flowed into closed depressions rather than out to the sea. Rivers may have been shorter, ending in lakes or inland sinks. The plateau may have had multiple drainage networks that were not yet integrated. For the Grand Canyon to be carved, a major through-going river had to exist. A river with a long path, a steep enough gradient, and a route to a lower base level. Base level is the lowest elevation a river can erode down to. Ultimately, base level is controlled by sea level. If a river can reach the ocean, it can keep cutting down until it approaches that level. If it cannot reach the ocean, its cutting power is limited, so the creation of the Grand Canyon required not only uplift, but the establishment of a drainage path that allowed water to escape. Once that path existed, the river gained permission to cut deep. It could carve downward because it had somewhere to send the debris. It could cut a canyon because it could export rock out of the system. That is why the formation of the canyon is tied to the integration of the Colorado River system. When smaller river networks connected into a single larger river, the cutting began in earnest. And because the plateau was high, the cutting was rapid by geological standards. The Colorado River did not just scratch the surface, it drilled. It cut down through sandstone cliffs, through limestone shelves, through shale slopes, through layer after layer of Earth's history, exposing them to the sky. And as it did, it created something that looks like a static monument, but is actually the result of continuous motion. Because uplift did not stop once carving began. The plateau continued to rise even as the river cut downward. This is another key dynamic. If the land rises and the river cuts at the same time, the canyon deepens dramatically. The river is chasing equilibrium, the land is pulling away, and the canyon becomes the record of that chase. This is why the Grand Canyon is so deep. It is not only that the river cut down, it is that the land rose while it cut. The river had to keep cutting to maintain its path. And over millions of years, that persistence created one of the greatest canyons on Earth. But there is a reason the canyon is not simply a narrow trench. Because the river is not the only thing working. The canyon widens through collapse. Rockfalls and landslides peel away the walls. Weathering breaks down cliffs. Freeze-thaw cycles pry cracks open. Rainstorms trigger debris flows that pour into side canyons. Tributaries carve into the plateau, feeding the main canyon with new sediment and widening the system. The canyon is carved from below and dismantled from the sides. It is shaped by water and gravity working together. The uplift of the Colorado Plateau made all of this possible. It created the elevation. It created the gradients. It created the instability. It turned a stack of ancient layers into a landscape vulnerable to incision. And once the river began cutting, the canyon became inevitable, not in a single moment, not as a dramatic collapse, but as a long-term consequence of physics. Time allows small changes to become enormous. This is the real power behind the Grand Canyon, not mystery, not magic, just the Earth operating on its own scale. A scale so large that it can be difficult to feel, but the canyon forces you to feel it anyway. Because when you stand at the rim, you are standing above a landscape that was not simply carved. It was earned. It was produced by uplift, by erosion, by climate, by sediment, by the persistence of a river that refused to be diverted, and by a plateau that rose high enough to let that river do its work. The Colorado Plateau lifted the stage, and once it did, the story moved from quiet accumulation to active carving. In the next chapter, we will follow the river itself, how it formed, how it connected across the plateau, and how a seemingly ordinary flow of water became one of the greatest geological sculptors on Earth. Because the canyon is not only the product of uplift, it is the product of a river that found its path, and never stopped cutting. A river cut through rock. Simple, clean, a straightforward story. But rivers are not born as giants. They do not appear fully formed, already powerful enough to slice through a plateau thousands of feet thick. They develop. They evolve. They change course. They merge with other streams. They capture new territory. They are shaped by the landscapes they cross, and in turn, they reshape those landscapes. The Colorado River is no exception. Before it carved the Grand Canyon, it had to become the Colorado River. It had to assemble itself from smaller pieces. It had to find a path across a rising plateau. It had to connect its headwaters to a distant base level. And it had to persist long enough, with enough energy and sediment, to cut through one of the thickest and most resistant stacks of rock on Earth. That is what makes the Colorado River so important. Not because it is the largest river in North America, it is not. Not because it carries the most water, it does not. But because it accomplished something far beyond what its size suggests. It became a sculptor of continents. At first glance, the Colorado River can feel almost underwhelming compared to the scale of the canyon. From the rim, it is hidden far below. From many viewpoints, it is invisible, tucked into the shadows of the inner gorge. Even when you reach it, standing beside it at the bottom, it can seem narrow, confined, and surprisingly ordinary. It is moving water, brown or green depending on sediment and season, sliding between rock walls. And yet, this river is the reason the Grand Canyon exists. Not as a passive presence, but as an active agent. Because a river is not just water. A river is energy in motion. Every drop is pulled downhill by gravity. Every current carries force. Every flood multiplies that force. Every grain of sediment in the flow becomes a tool, a grinding surface, a weapon. A river does not need to be wide to be powerful. It needs to be persistent. And the Colorado River has been persistent. But to understand how it became capable of carving the canyon, you have to understand what a river needs in order to cut rock. A river needs three things. First, it needs slope. Without slope, water spreads out and slows down. It deposits sediment instead of cutting. It becomes a builder rather than a destroyer. Second, it needs discharge. It needs enough water moving through the system to maintain flow over time, especially during wet seasons, snowmelt and storms. Third, it needs sediment, because the river does not cut rock with water alone. It cuts rock with abrasion, with sand and gravel grinding against the channel bed, with cobbles bouncing in the current during floods, with debris acting like sandpaper, scraping and hammering the rock into smaller pieces. The Colorado River had all three. It had slope because the plateau rose. It had discharge because its headwaters reached high mountains where snow and rain could feed it. And it had sediment because it flowed through landscapes rich in erodible rock, constantly supplying material to the channel. But there is still a deeper question. Where did the river come from? The modern Colorado River begins in the Rocky Mountains, where snowpack and alpine precipitation feed tributaries that merge into a single powerful drainage system. From there, the river flows southwest through canyons and plateaus, gathering water from additional tributaries before eventually reaching the Gulf of California. That is the modern path. But it was not always that way. In deep time, rivers are not fixed lines on a map. They are living systems. They can shift dramatically as landscapes change. They can be rerouted by uplift, blocked by volcanic flows, diverted by landslides, or reorganized by tectonic movement. For much of the past, the region that would become the Grand Canyon did not have a single integrated river system running through it. Instead, it likely contained multiple smaller drainage basins. Some flowed in different directions. Some ended in inland lakes. Some may have drained north or east. Some may have been trapped, unable to reach the sea. This matters because a river's cutting power is ultimately controlled by base level, the lowest point it can erode toward. If a river reaches the ocean, it can cut downward as long as the land is above sea level and the river has energy. It can export sediment out of the system. It can keep carving. If a river is trapped in an inland basin, its cutting is limited. Sediment piles up. Lakes form. The system becomes more about filling than cutting. So the Colorado River's greatest transformation was not simply gaining water. It was gaining an exit. This process is called integration, and it is one of the key turning points in the canyon's story. The Colorado River system integrated over time, as smaller basins connected, captured one another, and eventually formed a single route. This did not happen overnight. It happened through river capture, headward erosion, and changing gradients. River capture is one of the most dramatic ways a drainage system can change. Imagine two river systems separated by a ridge. One system has a steeper gradient and more erosive power. Over time it cuts backward, eroding upstream into the ridge. Eventually it breaks through and steals the headwaters of the neighboring system. The captured water is diverted into a new channel, strengthening the capturing river and weakening the captured one. Over millions of years, river capture can reorganize entire regions. It can create new drainage networks that did not exist before. This kind of process likely played a role in building the Colorado River system into something capable of carving the Grand Canyon. As the plateau uplifted and gradients increased, streams began to cut more aggressively. Channels deepened. Tributaries extended. Basins that were once separate became connected. Eventually, the Colorado River became a continuous line of flow across the plateau, and once it did, the carving began. But the river did not carve the canyon in a smooth, gentle way. It carved it through pulses, floods, seasonal surges, climatic shifts, moments when the river's power multiplied. Most of the time, rivers are quiet workers. They transport sediment. They shape channels slowly. They erode gradually. But during major floods, a river becomes something else. The water rises. The current accelerates. Sediment loads increase dramatically. Boulders that normally sit motionless on the bed begin to roll and bounce. The channel becomes a violent conveyor belt of rock, grinding against rock. This is when incision happens fastest. And over millions of years, the canyon was carved not only by constant flow, but by repeated extreme events. Every flood deepened the channel a little more. Every surge carried away debris that would otherwise protect the bedrock. Every storm and snowmelt season added another layer of erosion. And the river never had to be huge in the way people imagine. It only had to keep going, because time is the multiplier. A small force applied for long enough becomes unstoppable. But the river did not work alone. As it cut downward, the landscape responded. The walls became steeper. Rockfalls became more frequent. Side canyons formed as tributaries cut into the plateau and joined the main river. These tributaries are crucial. The Grand Canyon is not carved by one river alone. It is carved by an entire network. Streams and creeks, often dry most of the year, become violent during storms. Flash floods roar down narrow side canyons, carrying debris into the main canyon. These floods widen the canyon, carve side channels, and deliver sediment to the Colorado River. That sediment becomes the river's cutting tool. So the tributaries feed the river not only with water, but with abrasive material. They are part of the carving machine. And the canyon grows outward as the network expands. This is why the canyon has so many branching side canyons. It is not a single cut. It is a system, a drainage tree carved into stone. But there is another factor that makes the Colorado River uniquely effective. The river flows through a landscape with alternating hard and soft layers. Sandstone cliffs, limestone ledges, shale slopes. As the river cut downward, it encountered layers that resisted and layers that yielded. This created steps, nick points, waterfalls, and rapids. These features influence erosion. Where a river drops suddenly, its energy increases. Turbulence scours the bed. Erosion accelerates. Rapids form where hard rock creates uneven channels. Even today, the Colorado River's rapids in the Grand Canyon are often created by debris from landslides and rockfalls that constrict the channel, forcing water through narrow passages. In other words, the canyon creates obstacles for the river, and those obstacles create more erosion. The system feeds itself. Cutting creates steep walls. Steep walls collapse. Collapse creates rapids. Rapids increase erosion. Erosion deepens the canyon. It is a loop, and once it begins, it is difficult to stop. This is why the Grand Canyon is not simply the result of water running downhill. It is the result of a river interacting with uplift, rock type, climate, and gravity over immense spans of time. But the Colorado River's story is also a story of direction. Because there is an old question that has fascinated geologists for generations. Why does the Colorado River cut through the plateau instead of going around it? In many landscapes, rivers avoid high ground. They flow around mountains, not through them. But the Colorado River flows across the plateau and through the canyon, as if it refused to be diverted. The answer lies in timing. If a river establishes its course before uplift is complete, it can maintain that course as the land rises, cutting downward as it goes. This is called an antecedent river. The river is older than the uplift. It holds its path by cutting down as the land rises beneath it. Another possibility is that the river formed on top of younger sediments that once covered the region, then cut down through those sediments into the older rock below as the cover eroded away. This is called superposition. The river's path is inherited from a former surface, then imposed onto the deeper layers beneath. In reality, the Colorado River's development likely involved a complex combination of processes. And as uplift continued, the river responded the only way it could, by cutting down. That downward cutting is the beginning of the canyon. But the canyon did not appear instantly. At first, it would have been a valley, a deepening channel, then a gorge. Then, over time, as the river cut deeper and the walls collapsed outward, it became the vast canyon we see today. The Colorado River did not carve the Grand Canyon because it was extraordinary at the start. It carved the Grand Canyon because it became extraordinary through persistence, through integration, and through the energy granted to it by a rising plateau. It was given height. It was given slope. It was given time. And it used all of it. In the next chapter, we will follow the river into the heart of its greatest work, the actual carving of the canyon, the mechanics of erosion, the role of floods, landslides, and weathering, and how a river becomes capable of removing an entire landscape grain by grain. Because the Grand Canyon is not just the result of a river flowing. It is the result of a river cutting, and never stopping. If you could watch the Grand Canyon form in real time, it would not look like a disaster movie. There would be no single crack ripping across the land, no sudden collapse, no dramatic instant where the canyon appears. At first you might not notice anything at all. A river would flow through a high landscape. It would cut a little deeper each year. The walls would retreat almost invisibly. Rock would fall in small amounts, then in larger events. Storms would arrive and leave. Floods would surge and fade. The canyon would grow so slowly that a human lifetime would barely register the change. And yet, over millions of years, that slow motion becomes one of the most extreme transformations on Earth. The Grand Canyon is the result of erosion. But erosion is not one thing. It is a collection of processes working together, each one small on its own, but unstoppable in combination. The canyon was carved by water cutting downward, by rock breaking apart, by gravity pulling material into the river, and by the river carrying that material away. To understand how the canyon formed, you have to understand how a river actually cuts through stone. Because water alone is not enough. A river does not carve bedrock the way a knife cuts through wood. Water is not sharp, it is not rigid, it cannot slice. Instead, a river carves with force and friction. It carves with sediment. Every grain of sand, every pebble, every cobble carried in the current becomes part of the cutting mechanism. During normal flow, sand scours the bed like sandpaper. During floods, larger rocks begin to roll and bounce along the bottom, striking the bedrock, breaking off fragments, and grinding the channel deeper. This process is abrasion. It is one of the most important tools a river has. Another process is hydraulic action. When water moves fast through cracks and irregularities in bedrock, it creates pressure changes. It forces water into fractures, then pulls it out again. Over time, that repeated pressure can pry rock apart. It loosens blocks. It widens joints. It helps break the bed into pieces that can be carried away. A third process is corrosion, also called chemical weathering. Water can dissolve minerals, especially in limestone and other carbonate rocks. It can weaken rock over time, enlarging cracks and making it easier for physical erosion to do its work. But in the Grand Canyon, the dominant story is physical. The river cut the canyon by grinding it down. It did it with sediment, and that sediment came from everywhere. It came from the canyon walls collapsing. It came from tributaries delivering debris. It came from storms stripping loose material off slopes. It came from the plateau itself, feeding the river with a constant supply of sand and gravel. The river became a moving conveyor belt of erosion. But the Colorado River did not carve the canyon evenly. Erosion happens in bursts. Most of the time, rivers move sediment without dramatically changing their channels. But during major floods, the river becomes vastly more powerful. Water volume increases, velocity increases. The river's ability to pick up and transport heavy material increases dramatically. This is when the most aggressive carving happens. A flood turns the river into a machine. The channel scours deeper. Rapids intensify. Boulders move. Banks collapse. Sediment loads surge. The river becomes loud, violent, and unstoppable. Over millions of years, repeated floods did much of the heavy work of canyon carving. And those floods were shaped by climate. The Southwest is dry today, but it is not always dry in the same way. Over geological time, the region has experienced shifts in rainfall patterns, monsoon intensity, and snowmelt contributions from the Rockies. During cooler and wetter periods, rivers can carry more water. During warmer periods, storms can become more intense. During times of glacial advance in the high country, meltwater pulses can increase discharge. The Colorado River's history is tied to climate cycles that changed how often the river surged and how much sediment it carried. This is why the canyon is not just a product of uplift and water. It is also a product of weather, and weather in the canyon can be violent. Even today, the most dramatic erosion events often come from storms that never touch the river directly. A thunderstorm can strike the plateau miles away from the main channel. Rain falls hard on dry ground that cannot absorb it quickly. Water rushes downhill in sudden torrents. Small washes become roaring floods in minutes. These flash floods carry rocks, logs, mud, and debris into side canyons, carving them deeper and wider. They also deliver massive sediment pulses into the Colorado River. That sediment becomes the river's cutting tool. So the canyon is carved from two directions at once. The main river cuts downward. The tributaries cut inward. Together, they create the branching system that makes the canyon so immense. But erosion is not only about cutting. It is also about collapse. As the river cut deeper, the canyon walls grew taller and steeper. Steep walls are unstable. Gravity is always pulling them downward. The rock is always being stressed, always being weakened by weathering, always being tested by temperature changes. And eventually, pieces break free. Rockfalls are common in canyon landscapes. A crack widens. A slab detaches. A block tumbles down a cliff face and shatters into fragments. Those fragments accumulate in talus slopes at the base of cliffs. Sometimes the collapses are larger. Entire sections of wall can fail in landslides, sending huge volumes of rock into the canyon. These events matter because they widen the canyon. A river alone could cut a deep gorge, but to create a canyon as wide as the Grand Canyon, the walls must retreat. That retreat happens through mass wasting, the downslope movement of rock and sediment under gravity. Mass wasting includes rockfalls, landslides, debris flows, and slow creep. In the Grand Canyon, mass wasting is constant. It is happening even when the river is calm, and it is shaped by weathering processes that weaken rock over time. One of the most effective weathering processes is freeze-thaw. Water enters cracks in the rock. At night or during cold seasons, it freezes. Ice expands, pushing the crack wider. Then it melts, allowing more water in. The cycle repeats. Over time, this can pry apart solid rock. Even in a desert environment, freeze-thaw can be significant, especially at higher elevations and during colder periods in the past. Another major weathering process is thermal expansion. The canyon experiences extreme temperature swings. Rock heats up in the sun and expands. It cools at night and contracts. Repeated expansion and contraction can weaken rock, especially along fractures and bedding planes. Add rain, chemical weathering, biological activity, and gravity, and the canyon walls are constantly being prepared for collapse. The canyon is being dismantled from the sides, even as it is carved from below. This is why the canyon looks like it has architecture, because different rock layers respond differently. Hard layers form cliffs that stand tall until they fail in dramatic blocks. Softer layers erode into slopes, shedding material more continuously. The result is a stair-stepped landscape, where resistant layers create shelves and terraces, and weaker layers form ramps between them. This differential erosion is one of the reasons the Grand Canyon is so visually striking. It is not just a cut, it is a structure, a layered fortress of stone, shaped by strength and weakness. But the river's cutting is also influenced by what happens inside its channel. As the Colorado River incised, it created rapids and waterfalls, especially where hard rock resisted erosion or where landslides dumped debris into the channel. Rapids are not just scenic features, they are zones of concentrated energy. When water is forced through a narrow, uneven channel, turbulence increases. Turbulent flow is more erosive. It can scour the bed and banks more aggressively. It can move larger sediment. It can deepen the channel faster. In many cases, the most intense erosion happens where the river's energy is focused. So the canyon's shape is not carved at a uniform rate. Some sections cut faster, some slower, some widen more, some remain narrow. The river responds to rock type, debris, slope, and flow, and the canyon records that response. There is also the concept of nick points, steep drops or steps in a river profile. Nick points can form when a river encounters a harder layer of rock, when base level changes, or when tectonic uplift creates a sudden change in gradient. A nick point can migrate upstream over time, cutting downward as it moves, deepening the channel. This process can accelerate incision and contribute to rapid canyon development. In the Grand Canyon region, changes in base level, especially linked to the opening of pathways toward the Gulf of California, may have increased the river's ability to cut downward, driving incision upstream. When base level drops, a river responds by cutting down to match the new lower level. That is how rivers adjust. They carve downward until they reach a new equilibrium. And when the Colorado River gained a lower base level, it gained the ability to carve deeper. This is why the integration of the river system mattered so much. Once the river could export sediment out of the plateau and toward the sea, it could keep cutting, it could keep removing rock, it could keep deepening the canyon. The scale of removal is almost hard to believe. The Grand Canyon represents an enormous volume of rock that has been excavated and transported away, not in one event, but grain by grain, carried downstream, deposited in floodplains, deltas, and eventually the sea. The canyon is not just an empty space, it is missing material, and that missing material went somewhere. It became sediment far downstream. It became part of other landscapes. It became part of the ocean floor. The canyon is evidence of a massive transfer of rock from one place to another, driven by gravity and water over immense time. And through it all, The river kept cutting. It did not stop because the rock was hard. It did not stop because the canyon became deep. It did not stop because the landscape looked finished. Because rivers do not care what a landscape looks like. They respond to physics. As long as there is slope, as long as there is water, as long as there is sediment, the river will keep working. Even now, the Colorado River continues to shape the canyon. The rate is slower in some places. Human dams have changed the flow regime, reducing the frequency of natural floods that once carried massive sediment loads. But erosion still happens. Rockfalls still occur. Tributaries still deliver debris. Storms still carve side canyons. The canyon is still forming. It is not a relic. It is alive. The Grand Canyon exists because the Colorado River became a cutting force, because the plateau rose high enough to give it energy, and because erosion and collapse worked together to widen and deepen the landscape. This is the core mechanism. Water cuts down. Walls fall back. Sediment grinds the channel. Floods accelerate the process. Time multiplies everything. This is how a river creates a canyon. Not quickly, not dramatically, but relentlessly. In the next chapter, we will step into the present, looking at the Grand Canyon as it exists today, still changing, still eroding, still responding to climate and gravity, and still carrying the story forward. Because the canyon is not finished. It is still being carved, and the earth is still writing its next chapter. The Grand Canyon looks eternal. From the rim, it feels like a finished masterpiece, something that has always been there and always will be. The walls appear immovable. The cliffs seem permanent. The layers look as if they've been frozen in place for all time. But the canyon is not finished. It is still forming. Even now, even in the modern world of roads and viewpoints and trail maps, the same forces that created the canyon are still at work. Water is still cutting. Gravity is still pulling. Heat and cold are still breaking rock apart. Storms are still carving side canyons. The Colorado River is still moving sediment downstream. The Grand Canyon is not a monument in the way we usually mean it. It is a living landscape, and it is changing in ways most people never notice. The first reason the canyon still changes is simple. The river still flows. The Colorado River continues to move through the canyon, following the path it established long ago. It still carries sediment. It still erodes its channel. It still responds to storms, seasonal shifts, and the physics of gravity. But the river's behavior today is not exactly the same as it was in the past. For most of the canyon's history, the Colorado River was wild. Its flow rose and fell naturally. Floods surged through the canyon, sometimes massive, carrying enormous sediment loads and reshaping sandbars, rapids, and channel edges. The river's energy was uneven, unpredictable, and often violent. In the modern era, dams upstream have changed that rhythm. They have reduced the frequency of large natural floods. They have trapped sediment that would have traveled downstream. They have altered water temperature and seasonal flow patterns. This matters because rivers carve not only through water but through sediment. When sediment supply changes, erosion changes. When flood behavior changes, channel dynamics change. So the canyon's modern river is still powerful, but it is not identical to the river that did much of the carving. And yet, even with human influence, the river continues to shape the canyon. It continues to wear down bedrock in the channel. It continues to transport sand and gravel. It continues to erode banks and rebuild them. It continues to respond to every obstruction, every landslide deposit, every constriction in the channel. In some places, the river is still actively deepening its path. In other places, it is mostly maintaining it. But the river is only one part of the canyon's ongoing motion. The canyon walls are moving too, not by sliding sideways in a visible way, but by slowly retreating. This retreat happens through mass wasting, the downhill movement of rock and sediment under gravity. It includes rockfalls, landslides, debris flows, and the slow collapse of slopes. Mass wasting is one of the most important reasons the Grand Canyon is so wide. A river can cut a deep gorge, but to create a canyon this broad, the walls must fall back over time. And they do. Every year rock breaks loose. Sometimes the events are small. Pebbles and dust falling from ledges, thin slabs flaking off cliffs, minor rockfalls that leave fresh scars on the walls. Other times the events are dramatic. Large blocks detach from cliffs and crash down into the canyon. Landslides send entire sections of slope into the depths. Debris flows surge down side canyons during storms, carrying mud, rocks, and trees into the main canyon. These events can change the landscape quickly on a human timescale. A single rockfall can alter a trail. A landslide can block a side canyon. A debris flow can create new deposits at the river's edge. But even the dramatic events are part of a larger pattern. The canyon walls are always weakening, always being prepared for failure, because the canyon is a harsh environment for rock. The temperature swings are intense. The sun heats exposed stone during the day, and nights can cool it rapidly. This repeated heating and cooling causes thermal expansion and contraction, which stresses rock over time and widens fractures. Water also plays a constant role, even in a desert environment. Rain enters cracks, it dissolves minerals, it carries fine sediment into fractures. In colder conditions, it freezes and expands, forcing cracks wider. This freeze-thaw process can be especially powerful at higher elevations and during colder periods of the year. Over long spans of time, it acts like a wedge. It pries the canyon walls apart, and once fractures widen enough, gravity does the rest. Rock breaks free. It falls. It accumulates as talus at the base of cliffs, and over time, the cliff retreats. This is the slow widening of the canyon, a retreat that never truly stops. The canyon's tributaries also remain active. Most of the side canyons in the Grand Canyon are dry for much of the year. They look quiet, even lifeless. Narrow channels lined with sand and stones, steep walls rising on either side. But when storms arrive, these dry channels can transform instantly. Flash floods race down the tributaries with incredible force. Water that falls miles away converges into narrow slots, accelerating as it goes. These floods carry rocks and debris, scouring the channel bed, carving deeper, widening the walls, and delivering sediment into the Colorado River. This is why the canyon continues to grow outward. The tributary network is still expanding. It is still eating into the plateau. It is still widening the canyon system. The Grand Canyon is not one canyon. It is a branching system of erosion, a network of cuts that continues to develop as long as water and gravity remain in motion. Even the canyon's cliffs show that the landscape is still alive. Fresh rock surfaces appear where collapses have occurred. New talus slopes build up at the base of walls. Ancient landslide deposits remain visible, frozen in place, evidence of past failures that reshaped entire sections of the canyon. Some landslides in the canyon's history were so large they may have temporarily dammed the Colorado River, creating lakes upstream until the river cut through the debris. These are rare events, but they remind us that the canyon is capable of sudden change. Even in a landscape shaped mostly by slow processes, the Earth still has moments of dramatic movement. But the canyon's present-day story is not only about erosion, it is also about stability, because the canyon is shaped by a balance. Rock is being removed, but rock is also resisting. Some layers hold their shape for long periods. Thick limestone cliffs remain steep and intact until fractures reach a tipping point. Sandstone ledges persist for thousands of years before breaking. Resistant rock controls the canyon's architecture, forcing erosion to work around it. This is why the canyon's profile remains terraced. Hard layers form cliffs. Soft layers form slopes. This pattern continues to define the canyon's shape, and it will continue to do so as long as the rock stack remains. But time will change that too. Given enough time, cliffs retreat, terraces erode, buttes collapse, side canyons widen, the landscape becomes less sharp, less vertical, more subdued. This is what erosion ultimately does. It reduces relief. It lowers high places and fills low places. It smooths. The Grand Canyon exists because relief was created by uplift, but erosion always works to erase relief. In the far future, if uplift stopped completely and erosion continued uninterrupted, the canyon would eventually become a broad valley, less dramatic, more open, a landscape worn down toward equilibrium. That is the long-term direction of erosion. But uplift has not necessarily ended. The Colorado Plateau may still be rising in subtle ways. Tectonic forces continue to shape the region. The earth beneath the plateau is not inert. The deep mantle continues to move, and the crust continues to respond. Even small uplift over long spans of time can maintain relief and keep rivers cutting. This is why the canyon's future depends on a balance between uplift and erosion. If uplift continues, the river can keep incising. If uplift slows or stops, erosion will eventually dominate and the canyon will slowly lose its dramatic depth. But the canyon's present is also shaped by climate. The Southwest is not static. Rainfall patterns shift, droughts come and go, monsoon storms vary in intensity. Snowpack in the Rockies changes from year to year, affecting river discharge. Climate change, both natural and human-driven, influences how water moves through the system. More intense storms can increase flash flooding in tributaries, accelerating erosion in side canyons. Changes in snowmelt timing can alter the river's seasonal flow. Long droughts can reduce vegetation, making slopes more vulnerable to erosion when storms do arrive. The canyon is sensitive to these shifts because the canyon is a system, and systems respond. Even the smallest changes in water and sediment can have long-term consequences when multiplied across time. There is another way the canyon is still forming that is easy to overlook: wind. The Grand Canyon is not only carved by water. Wind is a constant sculptor here, especially on exposed surfaces and along rim areas. Wind moves sand. It abrades rock. It shapes small features, smoothing surfaces, creating pockets and hollows, polishing stone in subtle ways. Wind erosion does not carve the canyon's depth, but it contributes to the ongoing shaping of the landscape, especially in the drier upper regions. It is part of the background force, always present, always working. So the canyon today is not a finished object. It is a landscape in motion, a river still cutting, walls still retreating, tributaries still expanding, weather still breaking rock apart, gravity still pulling everything downward. The Grand Canyon is still being carved, even if the changes are too slow to notice from one visit to the next. And that is part of its power. Because it forces a different kind of perspective, it forces you to see the world not as fixed scenery, but as an active process. The canyon is proof that the earth is not still. It is always moving. And the canyon is one of the few places where that motion is visible, written into the walls in a way the human mind can actually read. Layer by layer, cliff by cliff, slope by slope. It is a reminder that even the most solid rock is temporary on geological timescales, and it is a reminder that the landscape we see today is only one frame in a much longer film. In the next chapter, we will step back from the mechanics and return to the meaning, because the Grand Canyon is not only a geological process, it is a record of Earth's deep past. A timeline exposed, a story carved into stone. And when you look into it, you are not just seeing a canyon, you are seeing time itself. The Grand Canyon does not end. Not in the way most stories end. There is no final chapter carved cleanly into the rock, no moment where the canyon is completed, polished, and left untouched. Because the canyon is not a finished object, it is a living record, a landscape still being written. But there is an ending of another kind, the kind that exists in the mind of anyone who stands at the rim and looks out across the immense space, across the cliffs and shadows, across the layers that descend into the earth like a staircase into deep time. It is the ending that comes when you realize what you are actually seeing. Not just a view, not just a place, but the history of a planet. The Grand Canyon is often described as one of the greatest natural wonders on Earth, a landmark of scale and beauty so extreme it feels unreal. But its true significance is not just visual, it is temporal, because the Grand Canyon is one of the few places on Earth where time becomes visible. Most of the time, the planet hides its age. Soil covers rock, forests cover hillsides, cities cover plains, oceans cover most of the surface. The Earth's history is buried beneath layers of the present. But here, the present has been cut away, and what remains is a vertical timeline of the past, a record of environments that no longer exist, a record of oceans that came and went, a record of deserts that marched across continents, a record of ancient collisions that built the foundation of North America, a record of uplift that raised the land high enough for a river to carve through it, and a record of erosion, relentless and patient, that exposed it all. When you look into the canyon, you are looking into a sequence of worlds. The top layers speak of younger deserts and coastal plains, environments that feel almost familiar. You can imagine wind shaping dunes, you can imagine rivers crossing flatlands, you can picture a landscape that resembles parts of the modern world. But as you look lower, the canyon carries you deeper into time. The layers shift, The colors change, the rock becomes older, the environments become more alien. You pass through limestones formed in warm, shallow seas, full of marine life that lived hundreds of millions of years ago. You pass through shales formed from quiet mud settling in water long gone. You pass through sandstones that once were beaches, dunes, or river channels. And at the bottom, the canyon reaches a world so old it almost stops feeling real. The Vishnu basement rocks. Metamorphic and igneous stone formed deep inside the earth nearly 2 billion years ago. They are the foundation of a continent. They represent a time before complex life, before oxygen-rich air, before the world had anything resembling the landscapes we know today. And the canyon exposes them, not as an abstract number, not as a concept in a textbook, but as real stone you can stand beside. That is what makes the canyon extraordinary. It is not just a geological feature. It is a physical connection to deep time, and deep time is difficult to truly feel. Humans are not built for it. We live in days and seasons. We measure time in calendars and decades. We think of history in centuries. Even the longest human stories are short on the scale of the earth. The Grand Canyon forces a different scale. It forces you to consider what millions of years actually mean. A million years is long enough for mountain ranges to rise and erode. It is long enough for climates to shift dramatically. It is long enough for oceans to move across continents. It is long enough for entire groups of organisms to appear, dominate, and vanish. The canyon holds hundreds of millions of years in its layers, and it holds nearly 2 billion years at its base. It is not just old, it is almost incomprehensibly old. But the canyon is not only a record of age, it is also a record of change. The story of the Grand Canyon is not a story of one environment enduring for ages. It is a story of transformation. The region changed from sea to land, from wet to dry, from shoreline to desert, again and again. And the rock layers preserve those transformations with quiet precision. A sandstone layer records a time when wind or waves moved sand across a surface. A shale layer records a time when calm water allowed mud to settle. A limestone layer records a time when marine life and carbonate sediments built up in warm seas. Each layer is a snapshot, a preserved moment of Earth's surface, stacked into a tower of time. Then, after the layers were built, the story changed again. The land rose. The Colorado Plateau lifted upward thousands of feet without breaking apart like a mountain belt. The layers remained mostly flat, raised into the sky like a platform. That uplift did something critical. It created potential energy. It made gravity matter more. It gave rivers power. And once rivers had power, the canyon became possible. But the canyon still needed a river capable of carving it. The Colorado River was not always the river we know today. It evolved, integrated, and established a path across the plateau. It gathered tributaries. It found an exit. It became a through-going system with a route to lower base level, and then it began to cut, not in a single moment, not in a dramatic collapse, but through persistence, through abrasion, through floods, through the grinding of sediment against bedrock. The river carved downward. The walls collapsed outward. Tributaries expanded inward. And over millions of years the canyon opened. The Grand Canyon is often described as a masterpiece of erosion. But erosion is not an artist in the human sense. It does not choose beauty. It follows rules. Water flows downhill. Gravity pulls rock downward. Sediment grinds. Weather breaks stone apart. Time multiplies everything. The canyon is beautiful because physics, over enough time, can create forms that appear intentional. But they are not. They are inevitable. That inevitability is one of the most powerful lessons the canyon offers. A river does not need to be enormous to reshape a continent. It needs time. A small force applied relentlessly becomes unstoppable. This is a truth that reaches beyond geology. The canyon is proof that persistence can produce the unimaginable. And the canyon also reminds us that the earth is not stable. We live as if the ground beneath us is permanent. We build cities and roads and borders as if the surface of the planet is fixed. But the canyon tells a different story. The earth rises. The earth erodes. The earth fractures. The earth changes. And it does not change according to human timelines. It changes according to its own. Even now, the canyon is still forming. Rockfalls still occur. Slopes still creep. Flash floods still carve tributaries. The river still moves sediment. The walls still retreat. The canyon is still being made. The process is slower than a human can easily perceive, but it is not slow to the earth. On geological timescales, the canyon is active, and in the far future, the canyon will not remain as it is today. Nothing does. Given enough time, the canyon will widen further. Cliffs will retreat. Buttes will collapse. Side canyons will expand. The landscape will continue to change. If uplift continues, the river will keep cutting. If uplift stops, erosion will eventually smooth the relief. The canyon's shape is not permanent. It is a phase, a moment in the planet's long history, a moment that humans are lucky enough to witness. That is why the Grand Canyon matters. Not because it is large, though it is. Not because it is famous, though it is. But because it is one of the few places where Earth's deep history becomes visible in a way the human mind can grasp. It turns abstract numbers into something physical. 2 billion years becomes a wall of dark stone. 500 million years becomes a stack of cliffs and slopes. Millions of years of erosion become a chasm so vast it changes the sky above it. And standing there, you cannot escape the realization that the Earth is not a backdrop to life. It is a participant. It shapes everything. It creates the conditions for ecosystems to exist. It changes those conditions. It destroys and rebuilds habitats. It moves continents, redirects rivers, raises mountains, and carves them down again. Life adapts, evolves, and disappears in response. The canyon is not just a geological record. It is an ecological record too. It reminds us that environments are temporary. Seas become deserts. Deserts become seas. Plains become plateaus. Plateaus become canyons. Nothing is fixed. And humans, for all our influence, are recent arrivals in this story. If you compress the entire history of the canyon's rocks into a single year, humanity appears in the final seconds of the last day. Our entire civilization would fit into a moment too small to see, and yet we stand at the rim and look down as if we are the main characters. The canyon corrects that illusion. It does not diminish human life. It places it in context. It reminds us that we live on an ancient planet, shaped by forces that will continue long after we are gone. And that realization can feel unsettling. But it can also feel grounding, because the canyon offers a kind of clarity. It shows that the world is bigger than the noise of daily life. It shows that time is deeper than we imagine. It shows that even the most dramatic changes can come from slow, persistent forces. The Grand Canyon is a place where the earth speaks plainly, not with words but with stone. A story written in layers, a story carved by water, a story lifted by tectonics. And when you leave the rim, when you turn away and walk back into the world of roads and buildings and schedules, the canyon remains behind you. But the perspective it gives does not have to stay there. Because the canyon is not just a landmark. It is a lesson, a reminder that the planet is alive in slow motion, a reminder that time is the greatest force on Earth, a reminder that beneath the surface of the everyday world, there is an ancient story still being written. And the Grand Canyon is where that story is exposed, waiting for anyone willing to look down into it and see what it truly is. Not just a canyon, but the Earth revealed.